So in this experiment, I'm going to be using red cabbage as a pH indicator. Um, Red cabbage is known to have a class of natural dyes in it known as anthocyanins. And anthocyanins structurally are just glycosides and acyl glycosides of anthocyanidins, which is just a term for a simple flavonoid ring system. Um, so we know that anthocyanins are actually water-soluble natural dyes, and because of this, they're able to be extracted by simply shredding up the red cabbage to increase the surface area, and then boiling it down for some extended period of time. I ended up boiling the red cabbage for about 20 minutes, and that was a sufficient amount of time to get a lot of the color out of the cabbage and create a relatively strong pigment inside the water. And then once the cabbage had been boiled down and there was sufficient pigmentation of the water that I used, I drained the red cabbage out to extract the dye. As you can see, I was able to get a fairly good amount of dye out of the cabbage, and then I will be showcasing the dye and this color as I begin doing the actual acid-base experiments with it. So to change the pH of this originally neutral, just water and anthocyanin solution, I'm going to be adding baking soda to the solution. Baking soda is known to be very alkaline, and therefore by adding it, we can effectively change the solution and make it basic with a pH above 7. So I do this just by adding the baking soda, and then of course I have to mix the baking soda into the actual solution. And you can see as I begin mixing the solution, it turns from the initial violet color of the neutral dye to the deeper blue that is associated with the basic form of the anthocyanin that was able to clearly be effectively extracted. Just a close-up of that blue color again. You can see it's clearly not the same violet that we had started with. So next, to test the acidic solution with the dye that I have extracted, what I'm going to do is I'm going to start with, again, the neutral anthocyanin dye. I'm going to be adding vinegar, which is known to be acidic. And as you can see, as I add the vinegar, the dye very rapidly changes from the violet color that was observed at the neutral pH to more of a pink-red color, which is associated with the acidic form of the anthocyanins that are found in red cabbage. So in terms of the actual color changes that we're observing with the anthocyanins, we first need to understand the reason for the coloration of the dyes in neutral conditions. So in neutral conditions, the anthocyanins have a very extensive conjugation system. This extensive conjugation system allows for a lot of electron delocalization, which in turn allows for the molecule to be very stable. Because of the heightened stability of this molecule, the highest occupied molecular orbital and the lowest unoccupied molecular orbital are separated by a very minimal amount of energy, or represented by the HOMO-LUMO gap. So because of this, pretty much an electron from the HOMO can be pretty easily excited to the LUMO using a specific amount of energy, right? So pretty much the decrease in the gap of the HOMO-LUMO due to the extensive conjugation causes an absorbance of a corresponding wavelength of light that is responsible for providing that energy. The light that is absorbed in this process causes the molecule to reflect the complementary color, which gives us the color of the dye. So in the neutral conditions, we see that the dye is more of a violet color, so we know that it must be absorbing a wavelength of light that corresponds to yellow. In the basic conditions, the hydroxy group of the neutral molecule is deprotonated. The deprotonation of this oxygen allows for a more stabilized resonance form between the ketone and this oxygen because the two molecules are more similar, which in turn increases the overall electron delocalization of the molecule, which again in turn increases the overall stability. So this increase in stability translates to a lower HOMO-LUMO gap. And the decreased energy needed to excite an electron from the HOMO to the LUMO gap corresponds to a increase in wavelength, as wavelength size or magnitude and energy are inversely related. So because a lower amount of energy is able to be absorbed and able to excite an electron from the HOMO to the LUMO, this corresponds to a greater wavelength being absorbed, which makes sense because uh, our dye, when we expose it to basic condition, turns blue, which means that it must be absorbing an orange color, which is a higher wavelength and thus a lower energy. So then we see that in the acidic conditions, the ketone group of what was the neutral molecule is actually going to be reduced to a hydroxy group, which decreases the conjugation system, and thus the overall resonance, delocalization, and stabilization of the molecule. So this in turn increases the energy of the molecule overall, and therefore increases the energy required to excite an electron from the HOMO to the LUMO. Beyond this, also the positive charge on the oxygen that's present within this heterocycle destabilizes the molecule, so this further increases the HOMO-LUMO gap. And because the HOMO-LUMO gap is increased, we know that the molecule must be able to, or needs to absorb a higher energy wavelength in order to excite an electron from the HOMO to the LUMO. And we see this represented as the molecule becomes acidic because it turns red, which we know means that it must be absorbing the complementary color green. Green is a lower wavelength than yellow, which the neutral molecule is absorbing. And because green is a lower wavelength and energy and wavelength are inversely related, we know that it is absorbing a higher energy. So in conclusion, red cabbage can be used as an effective pH indicator. The anthocyanins within red cabbage are specifically the molecules that are contributing to the ability to tell the pH. In this particular experiment, because we know that anthocyanins are water soluble, we simply boiled down the cabbage to extract it, but cabbage should be able to act as a pH indicator whether or not you boil it down. In conclusion, anthocyanins, they are highly stabilized molecules, and therefore they have a small or minimal sized HOMO-LUMO gap, and because of this, they can absorb a visible wavelength of light. As you expose it to acidic or basic conditions, this drastically changes the overall electron delocalization capacities of a given molecule, which changes the energy requirement to excite an electron from the HOMO to the LUMO gap. Because of the changes that are observed in acidic and basic conditions, being so easily visualized through changes in color, anthocyanin and therefore red cabbage in general can be used as a very effective pH indicator.